Last class we talked about the deadlocks and we continued until the resource allocation graph, and we talked about the three ways of handling the deadlocks. Method one is preventing and avoiding deadlocks. The second one is the system will able to detect whether there is a deadlock situation happened and to recover from it. And the third situation is pretending that we don't have like deadlocks will not happen in the operating system. So this third technique is the one used by most of the operating systems that we currently use, like Windows and Linux, for example. This class we are going to see preventing deadlocks, like avoiding deadlocks. So this is the one we are going to see today. Okay, so let's go into the deadlock prevention. So in deadlock prevention, this is the one we are talking about, the method one. You know, in the just now I was telling three methods to like kind of handling the deadlocks, and this is one of the method. Okay, we are going to discuss only that method, only one method. The other two we are not going to bother. Okay, so this is one of the method how to handle a deadlock. That's what we call deadlock prevention. Okay, and when we start the chapter, we talked about the conditions, 4 conditions. Like these conditions, if any of these conditions, at least one condition, if we don't have it, then we can prevent the deadlock, something like that. We saw it in the beginning of the chapter, and the 4 conditions are like mutual exclusion, hold and wait, no preemption, etc. So that's the thing we are going to discuss now. What the 4 condition is telling us, see, by ensuring at least one of the condition cannot hold. If we don't have at least one of these conditions, then there is no deadlock. That's the meaning of it. If any one condition occurs, then you will have a deadlock. Okay, if at least one of these condition is not hold, then we don't have deadlock. So that's the thing we are going to discuss now. Okay, see, in slide 2, this is the beginning of this chapter. For deadlock to occur, if deadlock is going to occur, then each of the 4 necessary condition must hold. Okay, ensuring at least one of these conditions cannot hold, then we prevent the occurrence of deadlock. That's the thing we are going to see. First one is mutual exclusion. The mutual exclusion condition must hold. That means at least one resource must be non-shareable. So let's keep at least one resource. That's what we call non-shareable. Non-shareable means like kind of if the resource is assigned to a process, nobody can share it. It's only by the process. It can only use it. So that's the meaning of non-shareable. Shareable resource do not require mutually exclusive access. Okay, and cannot be involved in the deadlock. For example, let's see, read-only files are good example of the shareable resource. Okay, read-only files mean to say we can read only. We are not going to write anything. Okay, that's one example of shareable resource. If several processes attempt to open a read-only file at the same time, they can be granted simultaneous access to the file. Okay, so let's assume that there are 2-3 processes, they want to have access to the read-only file. So simultaneously, they all get the access to open the file, use the file. Can you get the idea? So a process never needs to wait for a shareable resource. You get the idea? It's only read-only file. You get my point? So you won't have a deadlock situation. See, let's assume that you have a file. This is only a read-only. Read-only means you're not going to write anything. You're going to read data from this file only. So process P1, if it wants to access the read-only file, yeah, it can be granted. If let's say you have another process P2 and it wants to access the read-only file, so access is granted. So none of the process is waiting for P2 or P1 is not waiting for other process to release the resource. Do you get the idea? The process never needs to wait for a shareable resource. We are not going to wait for the shareable resource. Okay, do you get the idea? That's the meaning. Like if a process is waiting for a resource, that is held by another resource, sorry, another process, and that in turn waits for something else, then you have the deadlock. But here, process is not waiting for a shareable resource. Of course, it's a one way of avoiding deadlock. Okay, avoiding means preventing. And let's move on to hold and wait. Okay, this is another situation, another condition for deadlock to happen. Okay, so if we don't have hold and wait, there is no deadlock, is it? So ensure that the hold and wait condition never occurs. If you don't have hold and wait, no deadlock. So if you want to make sure that this hold and wait condition will never ever happen, so you need to guarantee that whenever a process requests a resource, okay, let's assume that you have a process P1. It may have some resource. Maybe let's assume that it has a resource R1 and it is requesting a resource R2. For example, let's assume that it wants I think in the last class I explained the directed edge, the meaning of the directed edge. You all know the meaning. If the directed edge comes from a process to the resource, it means it is requesting. If the directed edge comes from a resource to the process, that means it is holding. You know, this arrow means P1 is holding the resource R1. Or you can say, in other words, R1 is assigned to, allocated to P1. That's the meaning. If the edge is like this, it comes from a process to a resource, that means P1 is requesting an instance of the resource R2. Requesting, it's not yet allocated, it's just requesting. Okay, let's see the hold and wait. Let's assume this process is holding a resource and it is requesting another resource, for example. So whenever a process requests a resource, doesn't hold any other resources. Okay, so when P1 is requesting means make sure that it doesn't hold any other resources. Okay, so I will come back to the point. One protocol that we can use requires each process to request and be allocated all its resources before it starts the execution. So when P1 starts execution, you are going to assign all the required resources. Then only P1 can start its execution. Do you get the idea? If P1 is not ever receive any the required resources, it's not going to start its execution. Okay. Can you get the idea? So we need to have a protocol. So to make sure that if process P1 is requesting R2, when it can request, it should not hold another resource. Okay, see, whenever a process requests a resource, it does not hold any other resource, then you won't have this hold and wait situation. Okay, you won't have hold and wait situation when a process requests a resource. At the same time, it holds another resource. If this situation is there, you have hold and wait. If you don't have this situation, there is no hold and wait. Can you get the idea? So how to make sure this hold and wait is not going to happen? So just try to have a protocol, a procedure. So process is going to start its execution means it should be given all the resources. Then only it can start its execution. Okay. So we can implement this protocol by requiring that system calls requesting the resources for the process proceeds all other system calls. Because we have many system calls. System call for execute, system call for wait, system call for move to a ready state, system call for requesting a resource. There are many system calls process can issue. So the system call to request a resource should come first. All the system call make a request for a resource should be executed first, then other system calls will be executed. Okay, so let's go for another protocol, an alternative protocol for the hold and wait. Okay, it allows a process to request the resources only when it has none. Okay, only when it has none. It can, if a process doesn't have any resource, then it can request a resource. Like here, in this example, the one I draw here, process P1 is allocated with R1. Now it is requesting R2. So we can't do that. You get the idea? When a process does not have any resource, it can request a resource. When a process is holding a resource, it cannot request a resource. This is another alternative protocol to avoid hold and wait. Okay. A process may request some resource and use them. If it's going to request additional resource, it should release all the resources it is currently having. Like here, in this example, P1 is requesting R2. Here, it is requesting R2. If it wants R2, it should release R1. This one. It should release R1. Then only it can request a new resource. Okay. If we have this protocol, this procedure, we can make sure that we don't get this hold and wait situation. Either the first protocol or the second protocol. There are two procedures explained to avoid hold and wait situation. The next condition, the third condition is no preemption. So the third necessary condition for deadlock is there be no preemption. Preemption means, I told you already, releasing. So preemption of resource means releasing of resources. No releasing of resources that have already been allocated. So if there is no release, of course, you will have a deadlock. You get the idea? So if you want to make sure that this condition is not holding, you need to say we don't get this condition, we need to have a protocol. Protocol means a procedure. So what procedure? Let's assume a process is holding some resource and requesting another resource. And assume that that resource it's requesting, it can't be given immediately. Maybe somebody else is holding it. Okay, you get the idea? So let's assume the same situation. You have a process P1 and let's assume that it has a resource R1 and it is, wait a minute, and is requesting R2. It wants a resource R2. Let's assume that. So if a process is holding some resource, it is holding something. Remember, for resource we use a rectangular sign. For process we use a circle. Okay, for resource we use the rectangular sign. Okay, fine. Okay. Let's assume that a process is holding a resource and it's requesting another resource, and that another resource can't be immediately allocated for that. Mean to say P1 has to wait. In all the resources that process is currently holding need to be preempted. So let's see. P1 is having R1 and it's requesting R2. But R2 is currently given to somebody else. Somebody is holding R2. So in this case, whatever P1 has, preempt that one. What P1 has? P1 has R1. So you just preempt that, release that. You get the idea? So make sure that P1 releases whatever it has and then let the P1 wait for R2. Why not? No problem. You get the idea? Let the P1 wait for R2. Maybe R2 is used by somebody else. So let them finish with R2 and then it can be released and then it can be given to P1. You get the idea? That's what we call no preemption. So this situation will not happen if you have this procedure. Okay. So let's see in a simplified way. The resources are implicitly released. Okay, automatically. It's like automatically released. The preempted resources are added to the list of resources for which the process is waiting. The process will be restarted, only it can regain its old resources as well as the new one it is requesting. So P1, after R1 is given to P1, P1 can't continue because it wants R1 also. Okay, so it has to regain all its resources so that it can start executing. Can you get the idea? So in this way, when you have this protocol, you won't surely get deadlocks. For sure, you can avoid deadlocks. Okay then. So that's it. Deadlock situation will not happen if we have this protocol. So the protocol is when a process is going to request for a resource, it's not going to be assigned immediately. If it is going to be assigned immediately, fine. The protocol says if the resource, let's say P1 is requesting R2 and R2 is not going to be immediately given to P1, so let P1 release its resources. Okay, that's the protocol. Okay then. So let's see the last. Okay, we will just we'll just see alternative step for no preemption. Okay, let's see. If a process requests for some resources, we first check whether they are available. If they are available, fine, you can allocate the resource to the process. So there will be now no problem. You won't have any deadlocks or any issues, no worries. If the resources are not available, then check whether they are allocated to somebody else. Okay, and that somebody else is waiting for additional resource. So in this case, we need to preempt the desired resources from the waiting process. Whichever process waiting for a resource, they have to release all the resources allocated to them previously. Okay, you get the idea? So if the resources are neither available or held by some other waiting process, then the requesting process, it has to wait, of course. Okay, while it is waiting, some of the resources it has to preempt so that other process can use them, can request them and can use them. You get the idea? So this is the explanation of the situation, explanation of how the protocol is going to work. Okay. So by the way, we released the resources from the requesting process. But let's assume that requesting process has to restart only when it's allocated with the new resource. It is requesting and recovers all other previous resources which were preempted. While waiting, we preempted the resources, is it? So that resources has to be, it needs to recover those resources. It needs to get back those resources. Then the waiting processes can be restarted. Okay then. So this is about the no preemption. If you have the protocol, surely we won't have the deadlock. Okay. And the fourth condition is circular wait. Circular wait is one is waiting for somebody, one is waiting for something, and the something is with the other resource, process, and that other process waiting for something else, and that is that is occupied by somebody else. Can you get the idea? This is a circular wait condition. We saw it in the beginning of the chapter. So how to make sure you won't have a circular wait is, So one way to make sure is to impose a total ordering of all resource type and to require that each process request a resource in an increasing order of enumeration. Okay, so this is the condition. Let's see in detail. We'll go in detail. Okay, let's see. Let's assume you have these many resources, R1, R2, R3, R4, etc., etc. And we are going to assign to each resource type a unique integer number, like kind of an ID number. So each resource will get a unique number. Unique means it's different from each other resource, which allow us to compare two resources, okay, and to determine whether one precedes another in our ordering. Okay, so let's assume that each resource is having a unique number. Okay, then. So now we define one-to-one function, like R tends to R tends to N, R derives to N, means R is assigned to N. So where N is the set of natural number. For example, if the set of resource type R includes the tape drive, disk drive, printer, or whatever, so F tape drive is 1. That means the one resource for the tape drive. F disk type is 5, means we have 5 disk type disk drives, and then 12 printers. So let's assume this way. Okay, one-to-one function. Let's see. Now let's see the protocol. So now we every time we need to have a procedure to avoid that condition. So what is the protocol to avoid deadlock? Each process can request a resource only in the increasing order of the enumeration. Increasing order. That's a process can initially request any number of instances of a resource type. For example, P1 can request 2 instances of R1. Can you get the idea? Something like that. So after that, a process can request instance of the resource type if and only if that resource we have the number is bigger. For example, in the previous slide, I told you, I'll show you here. Where is it? Yeah, in the previous slide, I told you that tape drive we have 1, disk drive we have 5, and the printer we have 12 instances of printer. So whenever a process P1 requests a printer, let's say it requests 2 instances of printer, so that request number should be less than or equal to the total number of instances. We call it here N. N is the total number of instances. Okay, you get the idea? Make sure this point. So this is the one it's mentioned here. Okay. So for example, when using a function defined previously, a process that wants to use the tape drive or let's say printer at the same time, why not? No problem. But it first requests the tape drive and then it needs to request the printer. Why first tape drive? Why not the printer? You know, increasing order. Like which is having the smaller number of instances has to be requested first. Printer, we have 12 instances of printer. It can be requested later. Do you get the idea? The request has to be in increasing order. I mentioned somewhere. Yeah, here it is. Only in the increasing order. So which has the smaller number of instances that has to be requested first. Then the resource which has more instance later. Okay, then that's the idea. So we can require that a process requesting an instance of a resource, let's say Ri, it must be released to any resources. Okay, it must be released. It must have released any resources like Ri. Okay, because it has more instances, like 2, 3, 4, 5 instances. If these two protocols are used, you won't have a circular wait condition happens. Okay, you get the idea? So in this way, you can avoid circular wait situation. Remember, the protocol says We can request the resources only in an increasing order of enumeration. Okay, that is increasing order of enumeration. That's the protocol. Let's continue. Yeah. So we talked about the deadlock prevention. So it's a set of algorithms that prevent the deadlocks. How we have, like, we had many protocols, one for circular wait, one for no preemption, etc., etc. So we had certain algorithms. Algorithm here is something like techniques or procedures to limit the request. Okay, so if a process is holding a resource, it can't request a resource. If a process is holding a request and holding a resource and it's going to request another resource, that resource can't be immediately given. It needs to preempt the currently allocated resources, something like that. So the procedures are limiting the request. Okay, the limit ensures that at least one of the necessary conditions for deadlock cannot occur, like maybe no preemption occurs, no hold and wait occurs, or like circular wait occurs, something like that. The possible side effect of preventing the deadlocks by this method are low device utilization, reduced system throughput. Do you remember the meaning of throughput? We studied it in previous chapters. Throughput means number of tasks executed in a unit time. Like in 1 second, how many tasks are executed? So when we have these procedures to prevent deadlock, we are limiting the resource request. So what will happen? Resources will not be utilized that much and the throughput will be reduced a lot. Okay, so that is one drawback. I can say side effects or drawbacks of these deadlock prevention algorithms. So let's go for something else. Alternative one for avoiding the deadlock is to require additional information about how the resources are to be requested. So if you have the resource request, additional information about the resource request, we can try to avoid the deadlock. Okay, example. If a system with one tape drive and one printer, let's assume that we have one resource or one tape drive resource and one printer resource. And the system must need to know the process P will request first the tape drive and then printer. Okay, so if we know this in advance, then if let's assume that process Q will request first the printer and the tape drive, so we can easily assign and we can easily execute the process P and also the process Q. You get the idea. If we know what are the resources the process is going to request, accordingly we can plan the execution of the processes. Okay, let's see here. Let's say this P is going to request a tape drive first and then printer later. But let's assume that there is a process Q will request the printer first and the tape drive later. So it's okay, you won't have anything. You give the tape drive to P, at the same time give the printer to Q, and after they finish with the execution, release the resource and give the P printer and give the Q drive. You get the idea. So in this way, there won't be no deadlocks. How we can have this procedure? We need to know in advance what are the resources the process are be requested. Okay, do you get the idea? If you know some details in advance, we can have deadlock avoidance. We can try to avoid the deadlocks. So with this knowledge of the sequence of the request and release for each process, the system can decide for each request whether or not the process should wait or it's in order to avoid future deadlock. The operating system can decide. Is it the process is going to wait or it's going to end up in a deadlock situation or what? Something like that. Each request requires that in making this decision, the system consider the resources currently available. The resources currently allocated to each process and the future request, a future release of the process. So the system needs to have these details. What are the details it needs to know? What are the resources the processes currently holding? What are the resources the process going to request in future? Plus, what are the resources currently available at present? So if these details are known in advance, of course, we can have the deadlock avoidance. Okay. So next, let's assume that our operating system doesn't have deadlock prevention technique or deadlock avoidance technique, and deadlock situation will happen, of course, if your operating system doesn't have the prevention or avoidance algorithms. Of course, you may end up with deadlock. So let's have a system. If it has an algorithm that examines the state of the system to determine whether a deadlock occurred or not, and then it needs to have an algorithm to come back from the deadlock. So let's assume your operating system doesn't have a deadlock prevention algorithm or deadlock avoidance algorithm, doesn't have a prevention or avoidance algorithm. Never mind. If it has an algorithm to check whether the current state of the system is a deadlock situation, if as this operating system has an algorithm to recover, come back from the deadlock situation, yes, of course, we can manage with the deadlock. Even though if the operating system doesn't have prevention or avoidance algorithm, if it has these two algorithms, checking the current state for deadlock and recover back. If it has two algorithms, then of course we can come back from deadlock. We can recover from deadlock. Okay. So let's see those things. When we are going to detect an algorithm, so because I told you that we need to have two algorithms, one to detect, one to check the current state of the system, the second algorithm to recover from the deadlock. Okay, so for detection, when a detection algorithm determines that the deadlock happened, is existing, so several alternatives are available. Does it mean several alternative? One possibility is to inform the operator that the deadlock has occurred and let the operator deal with the deadlock manually. This is one way to recover from the deadlock. So the algorithm checks the current state of the system and it tells, yeah, deadlock occurs or deadlock not occurs. Okay, if deadlock not occurred, fine, that's fine, no problem. We don't have any issues. But if there is a deadlock, how to handle, how to recover back. Okay, there is an algorithm to recover back, but there are two options. One option is let the operator deal with the deadlock and come back manually. That is one possibility. Another possibility is system recover from the deadlock automatically. Let the operator recover from the deadlock or let the system recover from the deadlock. So these two options will break the deadlock. Okay, so one is simply to abort one or more process to break the circular wait. You know the abort system call. When a process is currently executing, even when you do something in your computer system, sometimes when you don't do it, it will ask you you want to retry or cancel. Do you remember? Some other task, when it hangs up, it gives you an option about the process or to continue or to skip. Do you get the idea? Abort means it will stop the execution. That will break the circular wait. So that's one thing. That is, the operator deal with the deadlock manually. So the operator, the user, stops the execution of the process. Okay. Or the second possibility is let the system recover. How the system recover? It has to preempt the resources from the deadlocked process. When you preempt the resources, maybe sometimes it will help. Okay, it will help to recover from the deadlock. For example, let's see one simple example. I hold the pen of Sarah. Sarah holds my pen. So this is a deadlock situation. So if I release my resource, let me give back Sarah's pen. Sarah can finish the execution and she will give back my resource. Can you get the idea? So I can get back my resource. If we release the preempt means release some resources from the deadlocked process, of course, the change. Okay, then we will continue back the deadlock recovery. As I mentioned before the meeting ends, so the idea for the deadlock recovery is we have an algorithm to detect the current state of the system, to know whether a deadlock situation exists. In case if deadlock exists, there are two ways to recover from the deadlock situation. One way to let the operator manually come back, recover back by means of abort system call. And another way is to do by the system. Let the system recover from the deadlock automatically. So to preempt some resources from one or more deadlocked resources and then recover back. Okay, so of course, when you preempt, the deadlock situation will resolve automatically. Automatically it will be resolved when you preempt the resources allocated to the deadlocked process. Okay, can you get the idea? So this is about chapter deadlock.